Before I get too far into this video, I did want to mention something I forgot to mention on the last one, and that if you go to the class website, you're going to notice that some of the links I've posted aren't to videos that I've created, they are to Khan Academy videos. I'm going to make an executive decision, which might be a poor one, but I'm going to say you are not required to watch those Khan Academy videos, but I do strongly recommend it just because I think it is a good idea to hear these ideas in a couple different ways and from a couple different people. So again, if you don't take notes on those videos, you won't be penalized, but I do strongly recommend that you do take a look at them just so you have some additional information to draw from. Alright, with that, I'm going to get started on this video, which is about some probability rules. One we already talked about on the last video, and that's simply that the probability of any event has to be somewhere between 0 and 1. There's no such thing as an event that happens less than never. There's also no such thing as an event that happens more than all the time. So probability has to be some value between 0 and 1, probability of any event. This second rule that I've written on this slide simply says that when you add up all of the probabilities in your sample space, you have to get a sum of 1. Said another way, that just means when you add up the probabilities of all the possible outcomes, and that's what your sample space represents, then of course you've covered all the possibilities, which means one of those events always has to happen. And if you sum up all your probabilities and one of them always has to happen, then that probability that you get when you sum all those things has to be 1. Basically, you could think of this in terms of flipping a coin. If you know that the probability of getting heads is a half and the probability of getting tails is a half, well then you add those two things together and you get 1. Because anytime you flip a coin, unless you have something absolutely crazy happen and it lands on its edge, which I don't think is physically possible, when you sum those two probabilities together, you're going to get a total sum of 1. The next idea we need to talk about is that of mutually exclusive events. These can also be referred to as disjoint events. And so you can see on the slide I've drawn they were supposed to be circles, but they're really just blobs. And they're two blobs that represent two different events, one labeled A and one labeled B. And you'll notice that this is really supposed to be a Venn diagram, but this shows that there's no overlap between our two events. So that's what it means that they're mutually exclusive. They never occur at the same time. So then there's actually a little relationship between two mutually exclusive events. And because they never happen at the same time, we can say that the probability that event A or event B happens is going to be the sum of the probability of A plus the probability of B. A quick example would be tossing a coin. The probability of getting, we'll call event A flipping heads, and we'll call event B flipping tails. Because of the way flipping a coin works, there's absolutely no way that both of those events can happen at the same time. You can't get both heads and tails. So the probability of getting heads or tails is, of course, just the probability of getting heads, which is 1/2, plus the probability of getting tails, which is 1/2. It won't always be the case that your two probabilities will sum to 1. That just happens to be unique to the example that I just gave. Here's another example, pretty simple. I've got some event A that has a probability of 0.3, and I have some event B that has a probability of 0.4, and because of the way their Venn diagrams are drawn and there's no overlap, then that means that they are mutually exclusive. So in order to calculate the probability of one or the other happening, all I have to do is add their probabilities. So the probability of event A or event B occurring is, of course, 0.7. When you're representing probabilities, it really makes no difference if you represent them as a decimal or a percent. Completely up to you. The next idea we need to talk about is what a complement is. When we talk about complements in terms of probability, we're not saying that we are being complementary to some sort of probability. We aren't saying anything nice about it. The complement of an event is simply 1 minus the probability that that event occurs. So it's all of the possibilities in the sample space exclusive of that event. So here's an example. I've got my event A, and you probably can't read it, but that's supposed to say that the probability of A is 0.8. I'll rewrite it down here. So we've already said before that the sum of all the events in our sample space has to be equal to 1. And that's where this idea of complement actually comes from. If the probability of event A is 0.8, then the probability of the events not in A, which would be 1 minus P of A, which I already have written up here, it's going to be 1 minus 0.8. And so, of course, that's 0.2. You just have to notice this notation here. Whenever we're talking about the complement of an event, we write this little superscript C. So that we just read this as the probability of the complement of event A is equal to 1 minus the probability of event A, which in this case is 1 minus 0.8, and of course that's equal to 0.2. So if event A has an 80% probability, then its complement has a 20% probability. Something else we need to mention is the idea of set notation. When we're talking about sets, we often will either want to join them with a union, which means or, we're saying is an element in one set or another. Or we may want to join the sets with an intersection, and that just means is there an element that is in both sets. We can use the same ideas with probability. The union idea, again that means or, would mean simply that we have the probability of event A or event B happening. Now notice instead of saying the word or in the notation, we can use the union symbol, which is pretty easy to remember because it just looks like a big U. So we would write the probability of event A or event B in the notation that I just wrote on the right side of the slide. If we're interested in the intersection of two events, meaning that both events occur, then I would write that as the probability of A and B, and then we use the intersect symbol, which simply looks like an upside down U. And if you have any easy way to remember that, share that with us, because I always just remembered it as the one that doesn't look like a U for union. So let's do, or actually on this slide I've rewritten that rule that we learned earlier about mutually exclusive events, just using this notation so you can see what it looks like. So before we said that if we have two mutually exclusive events, A and B, then the probability that if A or B occurs is the probability of A plus the probability of B. We can write that exact same statement by using this set notation, and instead of writing the word or, we use that union symbol. They mean exactly the same thing. So here on this slide I want to do a few examples for you. So I've got this Venn diagram, and as you can probably guess, Venn diagrams are going to show up somewhat frequently in this chapter because they provide a good visual representation for the various problems that we're going to be doing. So let's take a look. It says that in event A, you'll see that there are two sections that fall in event A. One has a probability of 0.4 and one has a probability of 0.1. So that means in this problem, the overall probability that event A occurs is of course 0.4 plus 0.1, so that's going to be 0.5. The probability that event B occurs then is the sum of the areas in point B, and in that case it's 0.4. And then the way we've got the diagram set up, we can see that there's a region where both events occur, where this overlap is in here. And so that is the probability that event A and event B occurs, which notice we're using that intersect symbol for that. And that probability is 0.1. And down here in this next example, we've got the complement notation. So this reads the probability of the complement of event A. Well, we know from just a moment ago that the probability of event A is 0.5. And so the probability of the complement of A is going to be 1 minus 0.5, which of course just so happens to also be 0.5. Similarly, if we want to find the probability of the complement of B, we can use the fact that we know the probability of B is 0.4. So we do 1 minus 0.4, and the probability of the complement of B would then be 0.6. Next, this notation might look a little bit insane, but what this is saying is that we want to find the probability of the complement of the intersection of events A and B. Well, the intersection of A and B we already found to be 0.1, so the probability of the complement of that would just be 1 minus 0.1, and that's of course 0.9. And this last one, I'm actually going to let you all ponder on a little bit. We'll talk more about this in a couple videos ahead. This says, what is the probability of A or B? So what's the probability of the union of the two? And I want you all to think about how we would figure that out. And like I said, we'll talk more about that calculation in subsequent lessons.